Today we're going to explore one of the most fascinating phenomena in food science: why cheese stretches into long strings instead of snapping like a brittle solid. This seemingly simple observation reveals deep principles about polymer physics and material science. Let's start with a fundamental question. What makes cheese different from other solids? When you pull on a piece of mozzarella, it stretches into long strings that can extend many times the original length before breaking. But if you pull on a cracker or a piece of chocolate, it snaps almost immediately. What's the difference? The answer lies in a property called viscoelasticity, which combines aspects of both viscous liquids and elastic solids. To understand viscoelasticity, we need to first understand the difference between elastic materials, viscous materials, and viscoelastic materials. An elastic material, like a rubber band, stores energy when deformed and returns to its original shape almost instantly when the stress is removed. The stress is directly proportional to strain. This is Hooke's law. Stress equals the elastic modulus times strain. A viscous material, like honey, dissipates energy as heat and flows continuously under stress. The stress is proportional to the rate of strain. This is Newton's law of viscosity. Stress equals viscosity times the strain rate. Viscoelastic materials like cheese exhibit both elastic and viscous behavior. They can store energy like a solid and dissipate energy like a liquid, depending on the timescale of deformation. One of the simplest models to understand viscoelastic behavior is the Maxwell model, which represents a material as a spring and dashpot in series. In the Maxwell model, the spring represents the elastic component with modulus E, and the dashpot represents the viscous component with viscosity eta. When you apply a force, both elements experience the same stress but different strains. The key parameter in the Maxwell model is the relaxation time, tau, which equals viscosity divided by modulus. Tau equals eta over E. This relaxation time determines how quickly the material responds to stress. Now let's ask an important question. What happens when we deform a viscoelastic material at different timescales? If you deform the material much faster than the relaxation time, it acts like an elastic solid. The spring dominates and the material stores energy. This is why cheese snaps if you pull it very quickly. If you deform the material much slower than the relaxation time, it acts like a viscous liquid. The dashpot dominates and the material flows. This is why cheese stretches when you pull it slowly. Now let's dive into the molecular structure of cheese to understand why it's viscoelastic. Cheese is fundamentally a network of proteins, primarily casein. Casein proteins are not simple spherical molecules. They form long, flexible chains that can be several hundred nanometers in length. These chains become entangled with each other, forming a network. Here's a simplified representation of the protein network in cheese. The green lines represent casein protein chains that are entangled and interacting through weak non-covalent bonds. The red dots represent cross-linking points, where proteins interact more strongly. Three types of molecular interactions hold this protein network together: hydrophobic interactions, electrostatic interactions, and calcium bridges. Hydrophobic interactions occur when nonpolar regions of the protein chains aggregate together to minimize contact with water. These are relatively weak, with energies around 1 to 5 kilojoules per mole. Electrostatic interactions happen between positively and negatively charged groups on the proteins. These can be stronger, around 10 to 20 kilojoules per mole. Calcium bridges are particularly important in cheese. Calcium ions, which are divalent, can simultaneously bind to negatively charged groups on two different protein chains, acting like molecular staples. These can have energies of 20 to 40 kilojoules per mole. Let's do a quick calculation to understand how fast these bonds break and reform. This will help us understand the relaxation time of cheese. The rate at which a molecular bond breaks can be estimated using the Arrhenius equation. The rate constant K equals a pre-exponential factor A times the exponential of minus the activation energy divided by Boltzmann's constant times temperature. Let's estimate the breaking rate for a hydrophobic interaction with activation energy around 3 kilojoules per mole, which is about 5 times 10 to the negative 21 joules per bond. EA approximately equals 5 times 10 to the negative 21 joules. At room temperature, 300 Kelvin, kBT, is about 4 times 10 to the negative 21 joules. Using a typical attempt frequency of 10 to the 8 per second, we get K approximately equals 10 to the 8 times the exponential of negative 1.25, which is about 3 times 10 to the 7 per second. This means that each individual hydrophobic interaction breaks and reforms about 30 million times per second. However, in the network, there are millions of such bonds working collectively. The effective relaxation time of the entire network is much longer, because many bonds must break simultaneously for large-scale deformation to occur. This collective behavior is what gives cheese its characteristic stretchiness. Another crucial concept in polymer physics is the entanglement molecular weight. This tells us how long a protein chain must be before it becomes entangled with others. For typical protein chains like casein, entanglement becomes significant when the molecular weight exceeds about 20 to 50 kilodaltons. Casein proteins are typically 20 to 25 kilodaltons, right at this threshold. When protein chains are entangled, they can't simply slide past each other freely. The entanglements act as temporary physical crosslinks that must be slowly disentangled during stretching. Here we see how entangled protein chains create a mesh-like network. When you pull on this network, the chains must gradually disentangle, which takes time and allows for stretching. Let's ask another important question. Why does the temperature of cheese dramatically affect its stretchiness? The answer has two parts. First, temperature affects the viscosity of the protein network. Higher temperature means faster molecular motion and lower viscosity. Viscosity is proportional to the exponential of activation energy divided by kBt. As temperature increases, viscosity decreases exponentially. Second, higher temperature provides more thermal energy to break the weak bonds holding the protein network together. This makes the network easier to deform. Cold cheese has high viscosity and strong intermolecular bonds. It behaves more like an elastic solid and tends to snap when pulled. Hot cheese has low viscosity and weaker bonds. It behaves more like a viscous liquid and stretches easily into long strings. Let's work through a quantitative example to estimate the relaxation time of mozzarella cheese at different temperatures. At refrigerator temperature around 5 degrees Celsius or 278 Kelvin, mozzarella has a viscosity of roughly 10 to the 5 Pascal seconds and an elastic modulus around 10 to the 4 pascals. The relaxation time is tau equals eta over E, which gives us 10 to the 5 divided by 10 to the 4 equal to 10 seconds. If you pull cold cheese quickly, say in under 1 second, which is much faster than the 10-second relaxation time, it acts elastic and snaps. At pizza temperature around 60 degrees Celsius or 333 Kelvin, the viscosity drops dramatically to around 10 to the 3 Pascal seconds, while the modulus decreases only slightly to about 10 to the 3 pascals. The relaxation time becomes tau equals 10 to the 3 divided by 10 to the 3 equal to 1 second. Now even relatively fast pulling, say over 2 or 3 seconds, is slow compared to the relaxation time, so the cheese stretches beautifully. We must also discuss two other critical components that affect cheese stretchiness: fat and moisture content. Moisture content acts as a plasticizer in the protein network. Water molecules insert themselves between protein chains, reducing intermolecular interactions and increasing chain mobility. More moisture generally means more stretch. Mozzarella, which is famous for stretching, typically contains 45 to 52% moisture by weight. This high moisture content is essential for its characteristic stretchiness. Fat globules, typically 1 to 10 micrometers in diameter, are dispersed throughout the protein network. They act as lubricants, allowing protein strands to slide past each other more easily during stretching. Low-fat cheese tends to be less stretchy and more brittle because there's less lubrication between protein strands. The protein network becomes more rigid and interconnected. Let's compare different types of cheese to see how composition affects stretchiness. This table shows 3 common cheeses. Mozzarella has high moisture and moderate fat, giving it very high stretchiness. Cheddar has moderate moisture and high fat, giving it medium stretchiness. Parmesan has low moisture, making it very brittle despite reasonable fat content. Notice that the key factor is moisture content, not just fat. Cheddar has more fat than mozzarella but is less stretchy because it has less moisture. The pH of cheese also matters significantly. At the isoelectric point of casein, around pH 4.6, Proteins have minimal net charge and aggregate strongly, reducing stretchiness. Most stretchy cheeses have pH around 5 to 5.5. Let's discuss a classic experiment that demonstrates viscoelastic behavior, the stress relaxation test. In a stress relaxation test, you suddenly stretch a material to a fixed strain and then hold it there while measuring how the stress changes over time. For a viscoelastic material like cheese, the stress starts high and then decays exponentially over time. This is because the viscous component allows the protein chains to gradually rearrange and relieve stress. The stress as a function of time equals the initial stress times the exponential of minus t over tau. The decay rate gives us the relaxation time directly. In contrast, for a purely elastic material like a rubber band, the stress would remain constant over time. For a purely viscous material, the stress would drop to zero almost immediately. For a more advanced understanding, we can consider the Reptation model, developed by Pierre-Gilles de Jong, which describes how long polymer chains move in an entangled network. In the Reptation model, a polymer chain is trapped in a tube formed by surrounding chains. It can only move forward or backward along its own contour, like a snake moving through grass. The green line shows a protein chain, and the red lines represent the tube formed by surrounding chains. The chain can only move forward or backward along this tube, which limits how quickly it can respond to stress. The time required for a chain to escape its tube scales as the molecular weight cubed. This strong dependence means that longer chains take much longer to relax. Tau reptation is proportional to m cubed, where m is the molecular weight. During aging, proteolytic enzymes break down long casein chains into shorter fragments. The cubic dependence on molecular weight means that even modest decreases in chain length dramatically reduce the relaxation time, making aged cheese more brittle. Let's calculate how much we can theoretically stretch cheese before it breaks. The maximum stretch ratio depends on how much individual protein chains can extend before breaking. For randomly coiled polymers, there's a maximum extension when the chain becomes fully stretched. A typical casein molecule contains about 200 amino acid residues. Each amino acid contributes roughly 0.36 nanometers to the extended chain length. The maximum extended length is Lmax equals 200 times 0.36 nanometers, which equals 72 nanometers. In the relaxed state, the protein chains are randomly coiled. The root mean square end-to-end distance for a random coil is proportional to the square root of the number of segments. L coil approximately equals the square root of n times the segment length, which gives us roughly 5 nanometers for casein. The maximum stretch ratio is lambda max equals L max divided by L coil, approximately 72 divided by 5, which equals about 14. This means individual protein chains can theoretically stretch to about 14 times their relaxed length. In practice, cheese typically breaks at stretch ratios of 3 to 5 because not all chains are perfectly aligned. Let's ask, what exactly happens at the molecular level when we stretch cheese? In stage 1, elastic deformation, the protein chains straighten slightly and weak bonds stretch. This is reversible. If you release the stress, the cheese returns to its original shape. In stage 2, as stress continues, chains begin to disentangle and slide past each other. Some weak bonds break and reform in new configurations. This is the stretching phase. In stage 3, continued stretching causes protein chains to become highly aligned in the direction of stress. The network becomes increasingly oriented. Finally, in stage 4, as chains approach their maximum extension, stronger bonds begin breaking irreversibly. Eventually, enough bonds break simultaneously that the cheese strand ruptures. This diagram shows the 4 stages. Stage 1 is slight deformation. Stage 2 is stretching with chain sliding. Stage 3 is high alignment and thinning. Stage 4 is breakage. There's an elegant dimensionless number that characterizes whether a material will behave as a solid or liquid, the Deborah number. The Deborah number equals the relaxation time of the material divided by the observation time or time scale of deformation. When the Deborah number is much greater than 1, the observation time is short compared to relaxation time, and the material behaves like a solid. When the Deborah number is much less than 1, the observation time is long compared to relaxation time, and the material behaves like a liquid. For optimal cheese stretching, we want a Deborah number around 0.1 to 1. This gives us the perfect balance between solid-like and liquid-like behavior. Let's consider the energetics of stretching cheese from a thermodynamic perspective. The work done during stretching is divided into two components: elastic energy storage and viscous energy dissipation. W total equals W elastic plus W dissipated. The elastic component stores energy that can be recovered if you release the cheese before it breaks. This is the energy stored in stretched bonds and straightened chains. The dissipated component is permanently lost as heat due to internal friction as chains slide past each other and bonds break and reform. The dissipated work equals the integral of viscosity times strain rate squared, integrated over volume and time. This viscous dissipation is why cheese actually feels slightly warm after vigorous stretching. The mechanical energy is converted to thermal energy. To better appreciate cheese's unique properties, let's compare it with other familiar materials. Glass has an enormously long relaxation time, over 10 to the 15 years, so it behaves as a solid on all practical timescales. Silly putty and hot cheese have similar relaxation times around 1 second, showing both solid and liquid behavior. Honey has a very short relaxation time and behaves as a liquid. Silly putty is the classic example of viscoelasticity. If you pull it slowly, it stretches. If you pull it quickly, it snaps. If you leave it sitting, it slowly flows into a puddle. Hot cheese behaves remarkably similar to silly putty. The physics is essentially the same, a network of long molecules that can disentangle over time. Let's discuss how understanding viscoelasticity helps in practical cheese making, particularly for mozzarella. First, the milk is acidified to pH 5.2 to 5.4. This is crucial because at this pH, calcium bonds are weakened but not destroyed, allowing for optimal stretch. Second, the curd is heated to 55 to 65 degrees Celsius. This temperature range gives the ideal viscosity for stretching. Too cold, and it's brittle. Too hot, and it becomes too fluid. Third, the curd is mechanically stretched and kneaded. This aligns the protein chains in the direction of stretch, creating the characteristic fibrous structure of mozzarella. This stretching process permanently changes the microstructure. The protein chains become oriented, and this orientation persists after cooling, which is why mozzarella has a stringy texture even when cold. Let's summarize the key concepts we've covered in this rigorous exploration of cheese physics. First, cheese is viscoelastic, meaning it combines properties of both elastic solids and viscous liquids. Second, the protein network formed by long entangled casein chains is responsible for the stretching behavior. Third, the relaxation time, determined by viscosity and elastic modulus, determines whether cheese behaves more like a solid or a liquid. Fourth, temperature dramatically affects both the viscosity and the strength of molecular interactions, making hot cheese much stretchier than cold cheese. Fifth, moisture acts as a plasticizer and fat provides lubrication, both modifying how easily the protein network can deform. Sixth, while individual bonds break and reform millions of times per second, the collective behavior of the network means that many bonds must break simultaneously for the cheese strand to fail. Seventh, the Deborah number provides a quantitative way to predict whether a material will act solid-like or liquid-like based on the time scale of observation. The stretching of cheese is a beautiful example of how complex macroscopic behavior emerges from simple molecular interactions. The physics of soft matter and viscoelasticity we've discussed here applies not just to cheese, but to many biological systems, including mucus, spider silk, and even the cytoskeleton of cells. Understanding relaxation times and how to control them through temperature, composition, and processing is key to designing materials with desired properties. Sometimes the most interesting physics is right in front of us, in everyday materials. Simple experiments like stretching cheese can reveal deep principles about polymer dynamics, thermodynamics, and material science. This is why food science is not just practical, but genuinely fascinating physics. Every bite of stretchy mozzarella is a demonstration of viscoelasticity, entanglement dynamics, and thermally activated molecular processes.